Hi, I'm Anjana. Hopefully you can hear me. This is my name in really big letters. You can find me on Twitter, and there's links there to my various other online presences. And yeah, I'd like to talk to you about programming paradigms today, or more specifically about programming across different paradigms. And I thought this was a fitting topic for PolyConf, because we've been learning about all these cool different languages and different technologies, different ways of looking at problems. And so what I'd like to do, and what I'd like to do with you, is kind of zoom out a little bit and get a little bit philosophical, because my background's not in computer science. My bachelor's is actually in philosophy, so I like to geek out on the philosophy stuff. So buckle up. That's what we're going to be doing. Just a little bit about me. I am an engineer at a company called Uber Research, no affiliation with Uber. And we do data about scientific research funding. And so I work mostly in Python on building a custom query language for interacting with our data on science research funding. And we're actually hiring. So if anybody is into Python and Pyramid and web development with that, come talk to me after. I am an alum of a couple really fabulous programming communities or tech communities that I've been so lucky to be involved with. One is called the Recurse Center. It's a 3-month self-directed programming retreat in New York City, and a really warm and wonderful programming community. And while I was at the Recurse Center in 2015 is where I was kind of mulling over all these different programming paradigms and started to learn about what were new to me paradigms like functional programming, and started thinking about how all these pieces interact. So a lot of what we're going to talk about right now I was thinking about when I was at the Recurse Center. And another program I was lucky to be a part of was Outreachy, which is an amazing initiative to get more women and underrepresented folks involved in open source by offering paid remote internships at organizations like Mozilla. So outreachy.org is a fabulous place to go or to send people if you know of anyone looking for a way to break into tech or to break into the open source world. Send them that way, outreachy.org. And I'm still involved with Mozilla, although my internship ended. I'm still a volunteer with the Tech Speakers program, so you can find me around at conferences quite frequently, and I have Mozilla stickers. So if you want one of those and you couldn't grab one downstairs, also come grab me. So yeah, more than happy to chat about any of this after the talk, but you're not here to talk about me. We're here to talk about programming. And when I was learning to program, and when I first encountered the notion of a programming paradigm, I started wondering, what it really meant and where it kind of came from. So I found out eventually that one of the first times that the idea of a programming paradigm kind of came to the public attention in the programming community was in 1978, when this guy, whose face is really big, named Robert Floyd, won the Turing Award, a little prize. And he decided to dedicate his Turing Award lecture and the subsequent paper, which you see the start of here, to the paradigms of programming. And I guess when you win a Turing Award, you're allowed to start your paper with a quote from the Oxford Dictionary, because that's what he does. But I always got yelled at for doing that. But anyway, he starts off by defining a paradigm as a pattern, or an exemplar, an example. I think pattern is kind of the most salient of those definitions. And he talks about paradigms as being these kind of, what we might think of now as more patterns of doing programming, things like structured programming or dynamic programming. He talks about these different ideas, different ways of approaching a problem. It's a little bit different from how we're going to look at programming paradigms in the rest of the talk, and I think how people generally frame the idea of a programming paradigm today. But I think that this paper, despite being from 1979, the year after he won the award in 78, is actually like really current and really relevant. And I love this quote from it. He says that, "I believe the best chance we have to improve the general practice of programming is to attend to our paradigms." So he really frames paradigms as being central to the entire discipline of programming. Not the language, not the algorithm, but the paradigm as being something that we should really focus on. And that's why we're talking about it right now. So my hope in this talk is that we just pay some attention to the paradigms that we use, the paradigms that we know, the paradigms that maybe we don't know so well. And we're going to go through some of the ones that we're probably familiar with and take a look at how they affect the code we write and the way we think about our code. And hopefully, when we leave, we will all have a little bit more motivation to keep attending to our paradigms. So this, of course, brings up the question, what are we talking about? I've used the word paradigm like 80,000 times already, and it's only minute 5 of the talk. What is it? What is a paradigm? So as I said, I studied philosophy, and when I first ran into the word paradigm, really big word, it was in a philosophy of science class where we read a book called The Structure of Scientific Revolutions by Thomas Kuhn. Anybody read it? Couple hands. Okay, cool. So Thomas Kuhn is basically like a historian of science, and at least in this book, he is kind of trying to give an account of how we make scientific progress as kind of a collective, as a civilization. And he centers the whole dialogue and his whole way of thinking about scientific progress around the notion of a paradigm. And the way he kind of puts forward a paradigm, one way of understanding it is that it's sort of like a worldview, a way of looking at the universe, the world around us. And if we're talking about it from a scientific perspective, it's a view of the world of the discipline that we're in as scientists. So if you're an astrophysicist, the universe is probably like the literal universe. And if you're maybe, I don't know, in the medical field, perhaps the world that you care about is the world of the human body, or perhaps populations of humans. As computer scientists, of course, the world that we'd be interested in would be computers and the programs that we run on them. So it's a way of understanding that whole domain. And another way of thinking about it is as kind of a model of that universe. A representation, a kind of symbolic shorthand for understanding how that universe ticks, what makes it work. And if it's a model, then of course that brings up a classic quote from a statistician, George Box, who said that all models are wrong. So it's important to keep in mind that a paradigm, this view of the world, view of the universe, is just an approximation. It is not how things actually work. It's just a model of how things work that helps us understand and helps us do science to better understand the world around us. And so Kuhn says that this model, this paradigm, isn't just telling us what's in the universe. It also tells us not just the theory, but also the methods and standards of a science together in an inextricable mixture. So these three things, theory, methods, and standards, all come out of a paradigm. What do we mean by that? Well, in theory, we mean what the universe is, what entities it's made up of, and how those entities behave and interact with each other. So what kind of system we're dealing with. And that's kind of what we would more typically think of when we look at a model and we see kind of what it tells us about the entities in the domain that it's trying to describe. But the other important thing that Kuhn noted that kind of follows along or sort of falls out from that model is what it means to make scientific progress. What methods we should use to try and understand things better. Another way we could understand that is like which questions we should ask, which questions it even makes sense to ask, or which questions are important to ask, which, again, we could understand as asking which problems are worth solving, which problems we should be focusing our attention on. And the standards by which we judge the quality of our work are also wrapped up in that. So this is kind of saying, okay, if we're figuring out in the methods what questions we should ask, in the standards we have an idea of what answers are good answers. And in this case, what solutions to the problems that we framed would qualify as good solutions. So all of this, the entire act of doing science, he says, is wrapped up in a paradigm. And in that sense, a paradigm, according to Kuhn, is necessary for scientific progress. It basically enables us to make progress. So the way he describes it is he talks about kind of a pre-paradigm dark age, like nothing is getting done. There's maybe someone over here who's got their own little mental model of the universe and is doing their own experiments, but they have completely no interaction with this other person over here who's got a different model, is asking different questions, getting different answers. We're all just kind of fumbling around in the dark. And as a collective, as a community, we're not really getting anywhere. Until a paradigm comes along that everyone in the community can, for whatever reason, or decides to rally behind and get on board with. And That theory, those methods, those standards allow us as a whole to collectively make work and advance our understanding of the universe in this model, in this paradigm. So for example, the paradigm of the Ptolemaic geocentric view of the cosmos, where the Earth is like this warm, bright, shining center of the entire universe, and all of the celestial bodies that we can see in the sky revolve around us, quite literally, in these celestial spheres. This is an example of a paradigm where it's a model. We know now that the model is wrong, but having this model enabled astronomers to reach some kind of consensus and collaborate together to make advances in their observations and give a structure to their work that allowed us to make some kind of progress on understanding the universe around us. But of course, as we just mentioned, this model is wrong. So there are going to be anomalies, there are going to be observations that scientists make while carrying out that progress that don't fit in the model. And what ends up happening is that first we try to shoehorn them in. You say like, okay, yeah, I noticed that Mars is going backwards, but that totally makes sense if we have like crazy epicycles, like orbits around orbits. And yeah, we can just keep adding circles until everything works out. And so this is what ends up happening. These anomalies, at first they kind of get crammed into the model that don't quite fit well in. But as enough of them accumulate, eventually they can no longer be ignored, and the community is sort of thrown into a state of crisis, where maybe the old guard is like, no, this paradigm is correct. It is the final answer to everything that we know about the universe, and we will keep adding epicycles. We will keep adding complicated mechanisms to explain the anomalies as long as we need to until everything is solved. And other people are saying, no, we can't keep holding to our old ideas. We need this new paradigm. And somebody else says, no, not that new paradigm, this other new paradigm, and blah, blah, blah. And there's just argument and chaos, and progress has kind of stopped at this point. We're all just arguing with each other. And this kind of continues until the notion that Kuhn is most famous for, paradigm shift, happens. So a new paradigm comes along that everybody can, again, more or less agree upon. So for example, the Copernican heliocentric model, where the idea is, okay, well, if we want to explain things like retrograde motion, wouldn't that be a lot easier if we just stopped clinging to our idea that the Earth is at the center of the universe and instead imagine that the sun is at the center and we are just on one of the spheres orbiting it? Then everything kind of falls into place, and the things that were anomalies in the old paradigm are no longer anomalous. They make sense. They fit nicely in our new model. And so this is then the new paradigm, the new model that allows progress to continue, but of course, it's still a model, it's not perfect. It becomes a new paradigm, it has new anomalies, a new period of crisis comes about, another shift happens, and so on and so forth forever, basically. It just continues in this cycle, he says. And so this is the idea of paradigms and how they enable progress and what they do for science, according to the Kuhnian view of things. But okay, this has been a lot of me like yapping about science and outdated astronomical models that we know don't work. So we're not here to talk about that. We're here to talk about programming. So let's get deep. What is it? What is programming? What are we doing? What are programs? What are computers? Why are we even here? What are we talking about? And this is kind of the answer that different programming paradigms, the question that different programming paradigms give us sort of different answers to. They give us different models of the world of programming. So if we think about the dark ages before computers, when like computers were like humans, like actual humans sitting down and doing computations and like looking up logarithms in like books and stuff, like this is a really dark age, right? None of us want to think about it. It was terrible. And then a miracle happened, and humans collectively as a civilization somehow figured out how to like electrocute a pile of rocks and make it do whatever we say, which is pretty awesome, and gave us all jobs, ultimately. And this led to kind of this new paradigm, imperative programming, where we give the computer commands. So the idea here is that programming is like telling the computer to do stuff. Imperatives, do this, do that, follow my commands, and follow them in the order I give them. Do this and then do that, and then do another thing. So in the imperative programming, we have this notion of like time being important, state, values changing. And we tell the computer, okay, like remember these values, like put these values in your little boxes in your brain and remember them and change them in ways that I ask you to, and then tell me what they are later. And so this command giving is kind of what the act of programming becomes in this paradigm. And I think it's helpful to have like visual mental models of things, because I'm a very visual learner. And as I said, also ex-philosophy student, so I like to have like meta, like models of models of models. And I think a useful metaphor, or kind of visual metaphor for imperative programming is a complex machine, like a clock or a watch. Because imperative programming sort of forces us to focus on the nitty-gritty, on like the intricate details of putting together a complex system, a complex machine that gives us the intended action, whether that's like turning hands on a clock. I think clocks are a good metaphor also because of the time notion in imperative programming state. But of course, like a clock, these intricate machines, that means we have to pay very, very close attention, and we have to be very precise about each individual component, each little tooth on each little cog in the machine. And if we mess up somewhere, or if we don't maintain this machine very well and it starts to corrode, it freezes up, it stops doing what we want, things stop working, we don't get the computer to do what we say. So this could be considered a type of anomaly or a situation that this paradigm doesn't handle very well. And so other paradigms came along that aimed to fix that or give a better solution to that type of problem, which is hard under imperative programming. So for example, object-oriented programming says, okay, this is too complicated once we try to create a really big machine. Like for little watches, it works okay, but if we're trying to make something really complex, there's too much going on. There's too many moving pieces. Keeping all of that state, all of those changing values all the time in our heads and in our programs, keeping all that straight is too hard. So let's divide it up into little chunks, which we'll call objects. And each little chunk will say, okay, you object, you keep a little part of the state of the program to yourself. That'll just be your responsibility. Just hide it from the rest of us, hide it from the rest of the objects, keep it to yourself. And then what we'll do is the rest of the program will send messages to you. So receive those messages, listen for them, watch, keep your eyes out for them. And when you get those messages, like depending on what state you have and what you know how to do, respond to them as you will. Now, I don't know about you, but this was a little bit different of an idea, of a way of thinking about object-oriented programming than what I was taught when I first learned object-oriented programming. I was taught it was all about classes and inheriting and like different types of mammals and these complicated taxonomies and UML diagrams and like blah. But we're going to come back to this a little bit later, but I think that a better way of conceiving of this is as the way that people like Alan Kay, one of the founding fathers of the paradigm, talk about it when he talks about the early days of Smalltalk and things like that. And this is based on this idea of hiding state in little chunks and sending messages back and forth. And so the visual metaphor, or the model of a model, that I think works for this paradigm comes from Alan Kay, who was a biology major, and he gives us a really nice biological metaphor of cells in a body as being kind of like an object-oriented program. The idea being that each object is kind of like a little cell, which has its own little state, like its little organelles and its little mitochondria and like whatever else is in a cell. I don't remember biology, but and they send messages back and forth, chemical messages, by passing molecules across their membranes. So a cell will receive a molecule at a particular receptor, it will ignore other molecules because it doesn't have receptors, and it will send out other molecules. And from that, these concepts of like little cells having their own responsibilities and sending messages, we get a nice complex system that's no longer as rigid as our mechanical imperative watch. It's flexible, it's more resilient. We don't have to worry about losing an individual cell, things like that. So this is, on one hand, a way we could consider object-oriented programming as a new model that solves some of the anomalies of imperative programming. But of course, it's not the only way of explaining some of those anomalies or getting rid of them. Another paradigm like functional programming might also have a good solution to some of those problems. So functional programming then takes the view, right, that like, okay, this complex watch with all of these moving pieces, that's like a lot of mutable state. That's super dangerous because if we do one little thing wrong and one cog moves a little lever in a way that another cog wasn't expecting, then like everything goes kaput. So mutable states, bad idea, but pure functions that just take inputs in and just return outputs out and do nothing else, those are safe because they don't mess with any other parts of the program. So if we just look at our programs as being pure functions that just take data in and return data out, and we look at those functions as being made up of other functions that just take data in and put data out, and those are made up of other functions that take data in and data out, then we have a much safer program that is sort of composed of smaller parts and is much easier to manage when we get to large levels of complexity. And so since this then has this very strong focus on data coming in and data going out, in functional programming, you start thinking of your program as being kind of like a pipeline of like transforming data from inputs to outputs. And I think a good visual metaphor for that is an assembly line, where you have kind of individual functions are sort of like individual stations on your assembly line. They take in, the first one takes in some raw material, some sheet metal, and assembles it into pieces of cars, and then the next one takes pieces of cars and assembles them into like the body of a car, and the next one takes some wheels and adds them on, so on and so forth until you get the desired output. And this is a very different way of thinking about a program than as a complex machine where you have to engineer every single little piece all to be working exactly at the same time together, or as a biological entity where cells are cooperating by sending messages back and forth. Very different model, but explains or solves some of the anomalies of imperative programming in another way, in its own way, which we'll return to in a moment. There's another programming paradigm that I want to talk about real quick, and that's the broader paradigm of declarative programming. So if imperative programming is like giving commands, right, like telling the computer do this and then do that, telling the computer exactly how to do, declarative programming takes the view that maybe for some situations, for some problems, that's a bit of an anomaly, like the fact that we have to be so focused on how we do everything. So declarative programming we could think of as saying like, maybe that's not the best way of modeling the universe. In some cases, maybe it's better to just model the universe in terms of what I want and not how you go about getting it for me. So in that case, programming becomes less about issuing commands in a certain order and more about making declarative statements about the world. So saying like, these are the facts that I know, these are things that are true, this is what I want from you, computer, lovely computer who does what I want, but I don't care how you do it. I just care that you give it to me. And I think, especially because one of the sub-paradigms of declarative programming is logic programming, I think a good visual metaphor for declarative programming is like a Sudoku puzzle. Any Sudoku fans? Wow, not a single Sudoku fan okay, 2, great. So for those of you who don't play or don't know Sudoku, it's like you have this 9x9 grid made up of 3x3 squares, and you have to have all of the digits 1 through 9 in each row, in each column, in each square. And in this metaphor, you are the computer, right? And the newspaper or whatever, the puzzle book of the Sudoku puzzle says, okay, here are the facts, here are the constraints of the world. You got to put all the digits in all of the rows. There's like a 1 in the top left corner, etc. Go. And you just have to fill out the puzzle. It doesn't care how you do it. It doesn't matter if you use pen or use pencil. It doesn't matter how you make guesses or what order you enter the numbers in. It just matters that you do it and that at the end of the day you've got a filled out grid that meets all of the criteria. So anyway, this has not been meant to be like an exhaustive tour of all of the paradigms, obviously. Just trying to think a little bit about how we can understand, how we can kind of crystallize these models for ourselves. But these are just some examples. They're by no means all of the paradigms out there, and they're not even the principal paradigms. So this guy named Peter Van Roy made a chart that I think was intended for this screen. And it goes through and categorizes all of the various principal programming paradigms as made up of different concepts and shows how the paradigms relate in terms of adding or subtracting a concept here and there, and gives some examples of languages that support those paradigms. And he writes, he's got a lot of writings about these things. But this is just to give you a sense of like how much we could spend time thinking and talking about programming paradigms. It's almost limitless. And one thing that I think that's interesting that you can see in this chart is that sometimes paradigms that we generally think of as being really diametrically opposed might actually not be that far apart. They might differ just by one or two concepts. And this brings me to another question. Like, when we're looking at any given paradigms, how different are they really? When I started, as I said, I wasn't always in tech, and when I started getting into the programming community, and I was exposed for the first time to these like epic battles between, like different language proponents and different paradigm users. And, you got like the functional programming people being like, ugh, OOP is so gross, like Java's for losers. And you've got the OOP people being like, whatever, Haskell's gross, like, ew, who wants all those weird symbols? Like, and then just, blah, blah, you're the worst, no, you're the worst, blah. Like, is this really necessary? What are we talking about here? What is the argument? So in particular with the paradigms of object-oriented programming and functional programming, I started wondering, like, how different are they? And I think in a certain light, we could actually see them as being really, really close. So if imperative programming, if one of the potential anomalies of imperative programming is this idea of shared mutable state, which we could represent as like having to manage all the complexity of this intricate machine all at once and know exactly where every wheel has to be at every moment. If that's an anomaly, then it's recognized by both the object-oriented and the functional paradigms. They both say this is a problem we need to solve. It's just that they do it in different ways. So functional programming is like, well, if we just make everything immutable, and you can't change state anymore, and there just isn't state, like values don't change over time, then you can share whatever you want. It doesn't matter, because you won't be able to mess up like somebody else's part of the code over there. And object-oriented programming just takes the other approach. It says, well, there's nothing inherently wrong with mutation as long as we protect it by keeping it safe in little units called objects, and we don't share it between them. And so I think this is kind of interesting because, again, there's two different ways of looking at it, but the basic thing they're trying to do is the same. And I mentioned earlier that this was kind of different than what I had learned about object-oriented programming. So this is a quote from Alan Kay on a, I guess now famous mailing list message, where he says he's sorry that he coined the term objects for what became to be known as object-oriented programming, because it gets many people to focus on the lesser idea. The big idea, he says, as we talked about earlier, is messaging. And so in this view of object-oriented programming, or this view of objects, an object is just something that's kind of defined by how it responds to messages. It takes messages in and it gives responses, whether that be changing something in its internal state or returning something, or who knows. Messages go in and responses come out. But functions, in a way, are similar because they're just things that take in inputs and give outputs. And one way of understanding a function, like a mathematical function, is just in terms of what output it gives for a given input. So there seems to be a similarity here in that they both seem to focus on the way things behave, at least if we zoom out and take a really big picture, broad view. And so one thing that really kind of blew my mind was when one of my batchmates at the Recurse Center, Darius Bacon, pointed out a similarity between the lambda calculus, which, it's got a lambda. Lambda's the logo of every functional language out there. It's super functional, right? Everything is a pure function. Untyped now, we're talking about untyped lambda calculus. And in the lambda calculus, since you only have pure functions, lambdas, you have to represent data as functions, as the way they behave. So a true is just something that, a Boolean value like true is just something that takes in an x thing, a first thing, and takes in a y thing, a second thing, and returns the first thing, the x. And false just takes the first thing and takes the second thing and returns the second thing. But this is actually almost exactly what Booleans look like in Smalltalk, which is the canonical, Alan Kay's, object-oriented language, very closely associated with the paradigm. In Smalltalk, a Boolean is also a thing that just takes two values, A and B, and the true gives you the first one and false gives you the second one. So there's clearly a similarity here when we think about the big picture of how these two paradigms conceive of or model a program and its components. So can't we all just chill out on the Reddit discussions? Jeez. Anyway, this question, which paradigm is the best, which people love arguing about? Yeah, I think you can see where I'm going with this. George Box, He says all models are wrong. No paradigm is the best. They're all terrible. No, they're all wonderful, depending on your glass half full, glass half empty outlook on things. But this isn't the end of his quote here. He doesn't just say all models are wrong. He says all models are wrong, but some are useful. And I would say that all programming paradigms are useful for certain things. So just like in physics, Einstein came along and with relativity provided an alternative paradigm to Newtonian classical mechanics that solved some of its anomalies. That didn't mean that we just threw out classical mechanics. It's still really useful for doing things like building bridges or like figuring out what happens when cars crash into each other or whatever. It's perhaps even more useful than like trying to use Einstein's theories to understand like very slow moving small objects. So when we think about models or when we think about paradigms, going back to George Box, he says the question to ask isn't, is the model true? Or like, is the paradigm good? It's, is the model illuminating and is it useful? What can it illuminate for us? What can it teach us? What can we learn from it? And so then this is the question, right? What can we learn from each paradigm? What can a given paradigm highlight for us that could be useful? So I think that what imperative programming, when you learn to code in it, it is really good at illuminating and kind of focusing on being explicit, saying exactly what you want to happen. And that focus on the implementation is something that's very useful when you're trying to think like a computer, because our poor little computers, they're sort of stuck in this paradigm a little bit, at least for now, until the next giant revolution. So if we want to be machine efficient, this is a really useful paradigm. And just this morning, we had a great talk about if you're working in Elixir, like a functional language, you might want to drop down to an imperative language like Rust to implement certain algorithms. So we saw this talk from Hans Elias about how we can use these nifty native implemented functions. I just really can't resist that joke today. Anyway, how we can use the NIFs that the Erlang VM allows us to deal with to bring imperative code into our functional Elixir code. Because sometimes you just need to implement an algorithm imperatively, and especially if you're doing things like complicated math and you want SOAP performance. Well, anyway, if that's what imperative programming illuminates, then declarative programming kind of is the complement to that. It sort of helps us understand how to be abstract and how to focus on the higher level domain and how to think about efficiency not in terms of how the machine would like to be efficient, but in terms of how humans are efficient and what is the clearest way for a human to express or to understand a problem at hand. So this is an example kind of taken from a book called Domain-Specific Languages by Martin Fowler and Rebecca Parsons. And this is one example of how when you're working in an object-oriented language, like Java, for example, it doesn't mean that you have to write object-oriented code. This is code that looks a lot more declarative because it's in what Fowler and Parsons call an embedded DSL, like a DSL that uses a subset of the host language's syntax. And so although this is Java, it's technically object-oriented, it really sort of seems more declarative. So what we're doing, we're making a calendar and we're saying, like, we're declaring certain facts about an event that we want to put on that calendar. We're not instructing the computer like how to remember the date and like how to store everything and what order to do things in. We don't care. For our human use of this calendar, it doesn't matter. We just want to declare information about it. So bringing some of these declarative principles into the code that you write in a different paradigm, like object-oriented Java here, can be useful if you're trying to focus on that big picture domain. So then, returning to our friend object-oriented programming, I think this is great at illuminating and teaching us the principles of, encapsulation, classic to the paradigm, and remembering things about the world, so state, that we need to for a given purpose. This is an example of bringing some object-oriented code into functional code. So it's from a blog post by Eric Tsarpales called Why OOP Matters in F#. So he's an F# programmer, F# being a language that's sort of multi-paradigm but functional first, allows you to do OOP, but in general, you'd tend to do functional programming in it. And But he points out in this article some great moments where it's a good idea to switch to object-oriented thinking. For example, if you're building an API that has to be aware of various dependencies, if you're doing this all as pure functions, you're going to have to pass around those dependencies all the time. And that can get cumbersome if you start to get into a large number of dependencies or a large number of functions. So sometimes it would just be easier and just easier to think about, easier to write, shorter, cleaner, to just wrap that all up in an object-oriented style into something that you can instantiate once with all of its dependencies, and then you can call the functions on it, the methods on it, that just, they remember those dependencies for themselves. You, as the programmer, don't have to remember them all the time. Now, of course, as we said before, there's similarities between functional programming and object-oriented. We could do this kind of thing with like closures and stuff, but that's, in a sense, even though that's a functional technique, it's sort of taking an object-oriented mentality of how we would go about constructing our code here. Now, of course, functional programming can also be really useful to bring into code you're writing in other paradigms, because it really puts the focus or illuminates these principles of isolation and of transforming data from inputs to outputs. I think a really good example of this is from a blog post, and there's kind of a related conference talk by Jessica Kerr, where she's talking about trying to diagram a new program on the whiteboard. I think she's writing it in Java or an object-oriented language like that. And she says that, so this diagram she starts writing on your left here, which is her thinking in an object-oriented style, she starts trying to plan out how the program's going to flow, and she realizes, okay, you have to make certain checks, and then you have to loop back over here if something is the case, and then you have to come back down over here. She gets this really convoluted, ugly kind of diagram that she also isn't sure, okay, if this is how the program works, how am I going to divvy that work up to the rest of my team? Because all of these components are kind of interconnected. Like, what am I supposed to do with that? And she says that when she switched to a functional way of thinking about things as transforming data, as flowing data through kind of pipelines or functions that just make small modifications to it in isolated ways, a much cleaner structure of the program just sort of fell into place, where she started thinking about the program as just having sources of inputs that the data gets filtered and combined together in some way and then comes out into whatever the output is that you want. And so this comes out with a much cleaner diagram, as you see on the right-hand side here. And that nature of functional programming that sort of focuses on isolating transformations to one small chunk of work at a time, that also means that it's easy to break this up, as you can see in the yellow boxes on the right-hand side diagram, to break this up into kind of isolated chunks, which you can just hand out to different people on the team and then put their work together all at the end, and you have a nice, clean structure that was easy to implement for your team. So the point here is that no matter what paradigm you're working in, there is probably something that you could learn or something that could be helpful from some other paradigm. And I think Peter Van Roy kind of sums things up nicely in an article so graciously titled Programming Paradigms for Dummies. He says that each paradigm supports a set of concepts that makes it the best for a certain kind of problem. And this is really the whole idea. All models are wrong, but some are useful, and each paradigm is useful for a certain kind of problem. None of them are best, absolutely. They're all just best in their own particular, the problems that they shine in. So one thing that Peter Van Roy stresses, and I think that we all at this conference can probably get on board with, is that learning lots of different languages, and especially working in multi-paradigm languages, gives you a wider range of options. Because then, if you want to bring in something useful from a different paradigm that would be a better fit for your problem, you don't necessarily have to switch the language you're working in or switch all the tooling, et cetera, et cetera. So he says that it can be a good idea to work in a language that gives you support for all these different tools so that you can then decide which one to use at any given moment. Okay, so I'm almost out of time here, and you're probably wondering, like, what is my point? Well, it's pretty simple, really. As we saw with Kuhn's work on understanding how science works, paradigms enable programming. We can't really do programming unless we have a model in our heads of what a program is and what it means to do the act of programming the computer, writing the code that the computer will run. once we've decided on one of those models, we can go forward, but we have to have some kind of model. And what that model is defines what programming means, what our lives as programmers look like, what we have to do. So when we're working in a given paradigm, I think it would be great if we could just embrace that paradigm for what it's good at, for what it does well, and not fight it and try to like shoehorn anomalies or things that it does badly into it. And instead, be open to shift our paradigm, try a new language or use a different feature of our language when it would be a better solution. So just to close out with a little more Floyd, he said in that same Turing Award lecture that the advancement of the general art of programming requires the continuing invention and elaboration of paradigms. So as a community, as a field, as a club of like super fun program friends, we need to come up with more paradigms. We need to keep inventing new ones. We need to keep trying things out. So like playing with things like the Zeta VM project, where you can create new languages and maybe do things differently. That's what we need to be working on. And at the same time, he says that advancement of the art of the individual programmer requires that they expand their repertory of paradigms. Well, he didn't exactly say that because he was a little confused about how pronouns and gender work in English, but I fixed it for him. He's just a Turing Award winner. He's not that smart. So the idea here is that as an individual programmer, we need to also expand our toolboxes, learn new paradigms, learn new ways of thinking, not just, let's say, new languages that use the same paradigms. And this is obviously a great place to do that kind of thing. So yay, congratulations. This is the whole point. We should just keep trying to learn new paradigms, keep trying to invent new paradigms, combine old ideas in different ways and come up with new ideas, and basically just attend to our paradigms. So thanks a lot. Just want to give a big shout out to some of the folks at the Recurse Center who helped me put this talk together and think about paradigms this way. And thanks to Polyconf for having me. I'm Anjana Vakil on Twitter, and here's a bunch of references. Thank you.